Hello, everyone. The time is now 3 o'clock. Welcome to SRIL Robotics Innovation Lab, workshop number 2, 3D Printing and CAD. My name is Clement, and on behalf of our entire team, thank you for joining us today. I would like to begin by acknowledging that this presentation is being transmitted from Surrey, British Columbia, Canada, on the traditional unceded territories of the Coast Salish peoples. Moving on. For the comfort and enjoyment of everyone here, I would like to remind everyone to please turn off their microphone and camera now for the duration of this presentation. We hope you enjoyed the 3D printing and CAD workshop.
All right, guys. Hi, everyone. My name is Daniel. So on the screen right now, we have a rough schedule for today's workshop. So we're going to start with the introduction to our organization, SRIL Robotics Innovation Lab. And then we're going to introduce our workshop leader for today, Adam. And then we'll go straight into his presentation. And we will wrap up with a Q&A period.
Hi, everyone. I'm Sophie, and I'm SRIL's president. SRIL is dedicated to empowering high school and university students in robotics and STEM. In addition to hosting this workshop series this summer, we are also developing a wide range of programs and resources. You can check out the resources and opportunities on our website, and starting from August 1st, tune in to our YouTube channel. Today's workshop will be led by Adam Metwally. Adam is a third-year standing undergraduate student in the BA and BASc Dual program at UBC, studying philosophy and mechanical engineering. He had the pleasure of spending almost 3 years with UBC Unmanned Aircraft Systems, a student design team focusing on pushing the boundaries of autonomous aviation. He spent 8 months learning from the best at WSP in Vancouver, working on large-scale building projects. Whether it's for club, school, work, or personal projects, Adam uses both CAD and rapid prototyping on a daily basis. These tools are absolutely critical to his projects. Let's give a warm welcome for Adam.
All right, hello everyone. Thank you all for joining us today. So I'm just going to share my screen real quick. Let's see what we got. All right, can everyone see my screen here? Yeah. Okay, I'm hoping so. So yeah, welcome everyone, and thank you, Sophie, for the introduction. So yeah, you are in a 3D printing and CAD workshop, and my name is Adam, so I guess we're on the right track. And for everyone's use today, we're going to be using Slido for Q&A. I won't be looking too heavily at the Zoom group chat. Unfortunately, I just find it a little bit distracting if I'm presenting or talking because they're kind of coming in. So if you guys do have questions during the presentation, I encourage you to go to sli.do, and the event code is 61879. And I will be checking that periodically throughout the presentation. So I definitely welcome questions. As well, if you see a similar question like yours, you have the ability to like it, and that will sort of allow me to see some of the most burning questions that people are having, or if I've missed something. So yeah, I'll leave that up for just a minute longer. But yeah, I believe I've put it in the Zoom group chat, ironically, as well. So if you have any questions, Slido 61879. Without further ado, let's go ahead and get started. So first, just a bit of an introduction and a little bit about the scope of the presentation. So like Sophie said, I am a year 3 undergraduate student at UBC and studying mechanical engineering and philosophy. I had the pleasure of being the captain of UBC Unmanned Aircraft Systems last year, coming up after being a mechanical designer. and a project lead dealing with radio communications. I also got a chance to work with WSP, working on some large-scale building projects as a mechanical engineering co-op student right after my second year. And this fall, I'll be starting my second, or I guess third technically, co-op term with Unilia Fuel Cells, testing fuel cells. So that's a bit about me. In my spare time, I also kind of enjoy lots of sports, boxing, soccer, hockey. So yeah, can find some common ground there, hopefully. Table of contents. So what we're sort of going to look at today. So this is kind of the order we're going to go in. So first things first, I know, you know, it is a CAD and 3D printing workshop, but I'm just going to sort of introduce you to the engineering design process a little bit, because I think it's very important as well to know where CAD and 3D printing and rapid prototyping as a whole fit into that engineering design process. So CAD and rapid prototyping aren't the whole of engineering and design, but it's very important knowing these tools and sort of where they fit in an engineer's day-to-day life and the work that they're doing. So yeah, by the end of this workshop, so just to give you a heads up of what you can expect, unfortunately, yeah, we're not going to all be 100%. I'm definitely not an expert myself in CAD and 3D printing. I do know a little bit about them. I've worked with them for 3-4 years now, so I can hopefully give a little bit of information on them, and you learn something through this workshop. But this is sort of a little bit where you should be hoping to get to. So you should have a general idea of what the engineering design process is and what it is and what the flow is. And you should have a general idea of where CAD fits within that mechanical design process. Another thing is a very brief introduction on how to get started with CAD. And you should have an idea of where rapid prototyping fits within the mechanical design process. Know at least 3 methods of rapid prototyping. We're going to cover a couple more, but I know it's going to be quite fast, so I'm hoping at least 3 of these methods sort of stick. And you should have a brief introduction on how to get started with 3D printing. So before we get straight into the material, just a quick check one. This workshop was sort of geared towards beginners, but I would just sort of like to get an idea of what sort of experience level people do have with CAD and 3D printing. So this presentation will hopefully be geared more towards people around A or B. If you're in the C category, there's 1 or 2 slides that might help you. If you're in the D category, to be honest, you probably would be teaching me. So yeah, I am hoping that this is going to be around A or B, maybe a couple people in C. So yeah, it looks like the results are coming in, and it's mostly A or B, which is good. So you're in the right spot. So yeah, we'll get into it. All right, so first of all, an introduction to the engineering design process. So what is the engineering design process? You know, what do engineers do? You know, what's common between the engineering professionals that, you know, are working on a day-to-day basis? So this process is a systematic method for approaching a vast array of engineering problems. Now, there's lots of definitions for it, but this is just one of them. I'd say it's one of one of the better definitions that are out there. So it's basically an iterative process, a circular process that you're pretty much running through, and it gives you an idea of when you have this problem, you know, how are you going to solve it? Where should you start, and where are you trying to get to? So this is a quote here. I really like this quote. So if you guys, I believe most of you are in high school, and if you're sort of going towards engineering or you're looking for a career in engineering, I remember back when I was in those shoes, it's sort of like, what exactly is an engineer doing? This quote pretty much sums it up, is that, you know, any idiot can build a bridge that stands, but it takes an engineer to build a bridge that barely stands. In a sense, engineering is taking these problems and merging science and business. You're trying to find that optimal point where you're able to basically design something that can help humanity and at the same time do so while benefiting a firm, because the firms are what are going to invest in these innovations that are helping humanity. So that pretty much that pretty much sums up a little bit of what engineering is. It's a very broad topic, and be kind of tough to sum it up, but hopefully that kind of helps. Engineering design process looks like. So you generally look something like this. Again, you can sort of name the steps differently, but it's first you're going to sort of define the problem, come up with specifications for the design or whatever you're going to use to sort of fix the problem. Then you're going to generate concepts, evaluate concepts, choose the best solution, develop it, test it, and implement it. And again, this is an iterative and a circular process. So you could be running from, maybe you're going to go specs first and you're going to develop a solution right away. And then, after that, you're going to see where it fails and use that to help you generate concepts and go back through it. That's totally fine. Maybe you want to start with testing an existing solution and then go back to defining the problem, et cetera, et cetera. But more or less, this is the general framework that engineers will use in their day-to-day lives to sort of, help their innovations and help their designing. So I think I have another quick check here as well. So if people want to go ahead and fill that out. Engineers' main purpose is to A, build bridges, B, use technical skills to design and develop solutions to all sorts of problems, C, do lots of math and physics, and D, invent gadgets. Yeah. So yeah, it looks like most people are getting it right here. The answer is B. They do, in general, do lots of math and physics. They do, in general, build bridges. Some engineers do that. And they do invent gadgets, technically. But the most important thing that they do, or what the general purpose of an engineer is they're going to use these technical skills. They're going to use math and physics and science and all this knowledge of manufacturing and how machines work and rapid prototyping and 3D printing and CAD and these technologies to design and develop solutions to all sorts of problems. So I'm just going to take a quick peek at the Slido really fast. Okay, perfect. So we do have one question here. What is the best CAD program for aerospace or mechanical engineering? That is a really good question, and we're actually going to touch on that a little bit later on in the presentation. So I will definitely come back to that question. So I'm just going to leave it in the Slido right now, and if it's not answered, then I'll make sure to come back to it. How much do you earn? I'm not 100% sure whether that's how much I respectively earn as a co-op student, or if whether that's like in general how much engineers earn. But I think Glassdoor is a website that would kind of help you. It would definitely depend on your field, your experience, and what industry. So even a mechanical engineer working in different industries could earn very different wages. But yeah. What is the best way to self-learn / pick up new CAD skills? Another question that I'm actually going to touch on a little bit later in the presentation. So again, I'll leave it here and come back to it. And how do we complete the quick checks? I believe that they should be popping up as polls on your screen in Zoom. So I think the polling feature will allow them to sort of pop up on there, and then you can just answer with A, B, C, or D. So hopefully that's, yeah, that'll help. Okay. Another quick check. So hopefully we can test our new knowledge there, how to complete them. The engineering design process only flows in one direction, and you cannot jump between stages. True or false? All right, again, a little bit less of a percentage, so about 85% of people got this one right as well. It is B, false. So the engineering design process, as we talked about, just going back a couple slides. Yeah, so it is a circular process, and if you have no idea where to start, you can definitely start from the top and go from find the problem. But a lot of time in engineering practice, you will end up starting in different places and jumping between the different stages. All right, good. So now the reason why you guys are here, we've sort of covered that engineering design process, but this is the bulk. This is what you guys are here for. So computer-aided design, or CAD, as a tool for mechanical design. So I'm going to be speaking respectively to mechanical design because that's sort of my background. But there is CAD available for electrical design. If you're looking at civil engineering, that's another one. And various types of engineering will cover them. But yeah, we're going to be looking at this, and there will definitely be overlap if you're going towards any of those other fields. All right, so what is CAD? So CAD, or computer-aided design, is a tool available to engineers in various disciplines. So it's going to assist them in a variety of these stages. It's one of the most popular technologies that's available now in our industry. And obviously its counterpart was drafting. So if you guys do go into engineering, like for example, mechanical engineering at UBC, which is where I study, you will actually have to take drafting courses during a practicum, excuse me, basically to learn how drafting was done back then, because those skills are actually used in CAD today. It's just CAD is basically a faster way of doing those things. So even back in the 1900s and when CAD wasn't available and engineers were completing their work, they were still using these same concepts, these same symbols, but they were doing it by hand, drawing designs but on 2D paper or actually sketching. So another thing that you would have to learn is sort of like how to sketch, because this is crucial to help communicate ideas between engineers. So in which stages does CAD help us is specifically starting at concept generation and running through to the implementation stages of design process. You know, obviously defining the problem and specifications aren't, like, you might use CAD, but it's probably not the best tool. And it's going to especially help once you get to generating concepts, evaluating concepts, and even through to testing solutions. So there are ways to test CAD models. So moving forward, I think I actually mentioned that here. Yes, I do. So what is CAD really? Like, how do we use it in practice? So CAD is used to generate 2D drawings or 3D models of intended or selected product models in order to communicate ideas between engineers. So like I said, in the past, they still needed to perform that communication. And they would basically, they would sketch those out, sketch out the ideas, or draw these legally binding drawings. So that's another thing, is that a lot of people will see CAD as sort of a way for 3D modeling. And if you're using it in the generate concept stage or the evaluate concept stage, it can absolutely sort of be like a way of almost making a visual sketch or a model to sort of show a consumer or a client, or maybe other engineers in your firm what you're thinking. But even when I was working at WSP, these CAD models that you ended up working on gradually became legally binding drawings that engineers would sign and seal, and they would be shipped off to the city, excuse me, to basically be approved for civil building permits. So CAD is basically, in essence, just a faster way of drawing and a more universal way of getting models and drawings done. But yes, it's important to note that CAD is not just design, but merely a tool for designers to use. So that's where that technical knowledge comes in. So I'm just going to take a quick peek at the Slido. Oh, yes, this is actually a good question. I will send the slideshow to the SRIL Robotics Innovation Lab, some of the admins there, and Sophie, and she will hopefully be able to communicate that to you guys if you want to be able to look at it for future reference. So that is true. Okay. Someone said say hi, so hi. Feel a bit like a puppet now, but all right. All right, so What does CAD look like? So CAD can be anything, again, from 3D models. So on the right here, we have a autonomous rover that I sort of helped design and build and manufacture back when I was with UBC Unmanned Aircraft Systems. And on the left is also a drawing from UBC Unmanned Aircraft Systems, which was a propeller adapter. So you can see that these have two very different sort of looks. Or model that basically used to communicate an idea. There's not necessarily as much rigid information used to be communicating, but it's sort of giving an idea of what this final product is actually going to look like when it's completed. Another thing that can be used, I think, as well, is I mentioned it here, is computer-aided engineering. So I don't have a ton of slides on CAE because it's a very, very complex topic. But sort of to give you an idea of what it is you can perform analytical studies. So if you guys have ever heard the terms FEA or CFD, which you might not have, and that's totally fine, but is basically a way to simulate these models and see how they would react in a physical world. So whether that's seeing how they deform with different forces or stresses put on them, or whether that's seeing how the pieces actually interact with each other, whether they're going to fit, how fast they're going to rotate, etc. So this model on the right was used for that kind of analysis, as well as just communicating ideas to some of our sponsors. On the left, however, this is a bit of a different design, and it's a 2D drawing that was essentially used to send to a machinist or a machine shop so that they could manufacture this part that we needed for our design. Or sorry, for our quadcopters. So for those of you who don't know, UBC UAS is a student design team at UBC that designs aircraft, autonomous drones or quadcopters. So this here was a part that essentially allows the propeller to thread onto the aircraft so that it doesn't come off during flight. So you can see here that you have these diameter 32 symbol, you know, the hole patterns, the threads, you know, how high this is going to make, and somebody is going to then take this drawing and they need to be able to understand, okay, so I'm going to go 12.5 down, and how critical is this dimension, etc. Okay, so we're going to go into another quick check. So CAD can be used for what? Modeling prototypes. I believe there should be a poll here somewhere. Apologies. There it is. Thank you. So yeah, so CAD can be used for A, modeling prototypes, B, communicating ideas, C, to create legally binding drawings, or D, all of the above. All right, answers are still coming in, so I'll just give it a couple more seconds here. Okay, so looks like we got 94% of people getting it right. So yes, it is all of the above, D. So CAD can be used for modeling prototypes. It can be used for communicating ideas. You might make a model purely just to communicate an idea. But yes, C can also to create legally binding drawings. So that whole range of things in between. Okay, I think I have one more quick check. That's correct. So true or false, CAD is a tool for designers. Okay, so looking at the answers coming in, so we got 85% of people getting it right at A, true. So we had 15% of people say false. So this actually was correct. So CAD is a tool for designers to use. It's not design in itself, and that's sort of like the point that I'm trying to make here. But yeah, it's just a tool that designers will use in their day-to-day life. All right. So actually, I think before I jump into, before I jump into this next slide, oh shoot, I'm going way ahead here. Okay, there we go. I'm actually going to take a couple questions from the Slido. So I still have a couple. So how does the university one attends for engineering impact their job prospects? It's a bit off topic, but yeah, definitely a good question. So I can go ahead and help out with that. I think in terms of engineering, if that's something that you're curious with, it definitely doesn't impact as much as other fields, is what I've found. So whether you're going to, UBC or UVic, Queens, Western, Waterloo, all great universities, even the ones that I didn't mention, I don't think anyone has necessarily a better advantage over another one. Like I don't think I've ever had an opportunity where I walked into a job and someone said, "Oh, you go to UBC, here's the job," kind of thing, or the other way around, like you go to UBC, get out. As well, like I don't think I've seen interview screeners sort of pick one out of the stack, unless maybe you're going to like a really high level Ivy League school like Stanford or something like that. I think more so what you might have is that the university that you're going to will have ties to industry locally. So, for example, UBC has a lot of ties to some of the local industries, such as Aspect Biosystems is a random company that comes to mind. Tesla actually has really good ties to UBC, so I do know a lot of colleagues who have gone off to intern or co-op at Tesla. For some reason, they just have a really good relationship with the West Coast and UBC. And we do get opportunities where Tesla will actually come visit design teams. So if that's something you're looking at, a lot of industry in the BC or lower mainland area is fuel cells or basically alternative energy, and as well biomedical. So if that's another thing you're looking at. But yeah, pretty much what I'm trying to say is that if a particular city has an industry that's kind of strong there, then the university will probably have ties through their co-op to local industry, and that's probably the advantage there. But the university name or going to a specific university definitely doesn't make you better suited for roles. So it's not something that you would 100% need to worry about. Say hi. I already did that. So I'm just going to mark that one as done. Yeah, so this is a good question, actually. So CAD covers both 2D and 3D, or in software terms, SolidWorks and AutoCAD. Yeah, so technically, CAD does cover both of those terms. So if someone were to say, I have a CAD model, they could have, AutoCAD, they could have a 2D model, or 2D model, quote unquote, which is basically a drawing. It could also be a SolidWorks 3D model, which I'm guessing is what you're meaning by saying like SolidWorks. It could definitely be both. You can also sort of, isolate the two terms. So if you're speaking typically 2D only, you could call it a drawing, which is typically something that you can kind of see. You can also call it in 3D a model. Another thing I didn't really mention in the presentation is BIM, or Building Information Modeling. This is used more in like civil engineering industries. So if people have heard of Revit, that's another Autodesk software, which I will talk about Autodesk. That sort of is in another category that's sort of related, but not necessarily CAD. But basically what CAD is referring to is anything that's a drawing or a representation or a sketch of an intended product or design that doesn't basically have information within the parts. It's just basically a superficial thing that you can look at or analyze. Can you use Git to work on CAD models? Yes, you can actually. I believe you can. I don't think multiple users will be able to contribute consecutively because merging the CAD models is a little difficult. But if you're talking about just using Git to store CAD models, I think you can. As opposed to using Git to work on CAD models, like so that multiple users can contribute consecutively, I actually do have a solution for that. That'll get answered, I think, on the very next slide, actually. Engineering, there are lots of good ones. UBC is a good one. I would definitely say they have their really big Mech 2 program. Is a really good experience, really enjoyed that experience, and very unique. Has really good reviews from the education sector, but other really good mechanical engineering schools, U of T is a really good one. I know McGill, but a lot of the universities in Canada sort of addressed with my other answer. I don't think it'll be a huge, so like say you're going to U of A for mechanical engineering, like I don't think you're gonna see a huge difference in the actual program. And that's just sort of because engineering is accredited. So most of these universities are actually required to sort of present the same content. UBC just does it in a different way with their Mech 2 program, and universities might do it in a different way, but you'll learn the same stuff. Okay, I'm going to, okay, one more question, and then I'm going to jump back to the presentation here. Engineers of what specialty help design machinery for hospitals and other healthcare sectors? And how does CAD and 3D printing help with that? This is actually a really good question. Engineers of various different specialties will work designing machinery. So mechanical engineering is one, but also electrical engineers, computer engineers working on the software, materials engineering perhaps. So yeah, you can definitely have a variety of disciplines, but CAD and 3D printing has massively helped those industries, particularly for simulation and design verification, that, you know, it would have been a lot trickier had you not been able to do these models. So while these technologies have sort of helped all industries, I think across the board, definitely biomedical is a good one. Okay, I'm just going to quickly jump back to the presentation here. And yeah, I do have my email at the end of this presentation if people have burning questions that I didn't manage to answer in Slido. Okay, so how can you get started with CAD? There are several industry level CAD software packages that are used. Some of you guys mentioned SolidWorks. Some of you guys mentioned AutoCAD, which is an Autodesk product. So other ones in there you might have heard of are Inventor, Fusion 360 from Autodesk. You guys may or may not have heard of Creo or Pro Engineer. They used to be called Pro Engineer, I believe. Or you may or may not have heard of Onshape. And there are more that I haven't listed here. And I think someone asked, what is the best one? So if you're interested in mechanical or aerospace. I think a lot of industries, so it kind of depends, even if you're a mechanical engineer, on what industry you're going into. A lot of startups I've seen will use Onshape. So Onshape is sort of a 3D, 3D modeling and a drawing software that's purely browser-based. It's sort of new. Actually, the original inventor, I believe, or one of the founders of SolidWorks actually spun off and made Onshape. And I think someone else also asked about keeping version control for CAD or keeping things organized. So that's actually called PDM, or I think it's Project Data Management is what that stands for. And Onshape also has built-in PDM. So that allows you to collaborate on a lot more documents, sort of have multiple people working on models at the same time. SolidWorks will also allow you to do this with their sort of proprietary, I think it's called SolidWorks PDM. And so that's an option that's available. The thing with SolidWorks is that it's a lot more expensive. So you'll find that a lot of bigger companies will use SolidWorks. You might also find companies, particularly in civil engineering related industries, will use Autodesk, particularly AutoCAD, Revit, and Inventor. As well, another one that sort of falls out of there is Fusion 360, which is sort of similar to Onshape in the sense that you're able to have built-in PDM. Creo, if you're interested in aerospace engineering, I believe that you see a lot of Creo being used. There's another software that I also see being used a lot, but I can't remember the name off the top of my head. And the main difference here is because surfacing in SolidWorks and Onshape is a lot trickier than in Creo. So automotive industries will also use Creo a lot more. So that's sort of an idea of the different CAD software packages. But the key that I want people to remember as well is that it's definitely never bad to just pick up really any CAD software that you have available. So if you have a high school that has one, UBC has sponsor from SolidWorks. So if you went there, other universities I'm sure have sponsorships from other different industry companies. But it's kind of like learning a language in the sense that if you learn one, learning more becomes definitely a lot easier. So picking up any of these, I believe Onshape is free to most students if you sign up for the education plan. So if you're interested in that, definitely pick that up. And I think what a lot of people are going to ask is, what should I make? So say you pick up Onshape, what are you going to make? So the greatest thing about CAD is that you can test and create a huge variety of systems. You can, test and design, anything in your house, like from a coffee mug to, I don't know, a pack of gum. It's kind of random. Or you could design like a car with CAD, it's just more parts and more things that are actually integrated together, but it's going to be the same principles. If you're looking for practice, one thing that I did when I was first starting getting out with CAD was basically just trying to model some of the objects around me, and that'll actually give you really good practice with various different CAD techniques. So whether you're say you're modeling a mug, for example, this is a really curved surface, so you might have to do a little bit of surfacing. You might have to deal with that. Whereas if you're designing a box and it's very rigid and flat, that might be a little bit easier, and you're going to take a different approach to modeling it. So if you're looking for practice, one thing is to just try and model simple objects around you. If you do have access to a 3D printer, and this is something again that we'll sort of cover a little bit later on in the presentation, as well as some basic electronics, there are actually some really cool projects you can make. So again, I'll send out the presentation with SRIL. But this link here actually has a bunch of mechatronics-y project ideas. So you can definitely go to that link and, say you have some basic electronics, making any of these is super useful. And as well, a lot of companies or firms, in addition to getting experience with cool projects, and that's fun for you as well, these are actually stuff that you can definitely put on your resume for sure later on to sort of show some of the experience that you have. So I do know that I think I saw 1 or 2 people respond with them having some decent experience with CAD. So if you do know CAD and you understand everything I'm meaning here, if you don't, that's totally fine. But definitely a few CAD tips for even the best CADders. Basically, always fully define your sketches. Working with other people, I've seen people not fully define their sketches, and that is totally fine, except when anything goes wrong in your part and you try and come back to your design and change it, and everything goes wrong. So please fully define your sketches. Always remember the manufacturing method you're planning to use while you design and draw. This is something that a lot of new people working with CAD don't really think about 100%. Definitely something I didn't think about when I was starting out with CAD. When you're designing and when you're drawing something, keep in mind how you're going to manufacture this part. If you're going to 3D print it, that opens you up to different ways of putting your piece together, rather than if you're going to, for example, water jet cut it or machine it, then that's going to be something completely different. So you got to make sure that what you're actually designing or drawing is actually possible. Always name all parts and assemblies. So this is similar to if people have programmed before, commenting your code. This is the same as on an exam, show your work. It's really important to actually name this, especially when you're collaborating with other people. if you don't name the things that you're making, the files, the parts, the assemblies, again, it's totally fine when you're making it at the time and then you come back, something goes wrong with your design, you need to come back to it and you look at it and you have absolutely no idea what happened. So definitely something that's important. And all things equal, the simpler method of creating a part is better. So the best people who are working with CAD are going to take the simplest and most efficient route to designing a part. Having something extremely complicated, again, when something goes wrong with that part, it makes it 10 times harder to fix. So check true or false, your CAD method should be as complex as possible. Okay, I think most people have answered here. So we're at 98% said false, which is the right answer. So quick check 7, true or false? CAD is limited to modeling only a select number of objects. Okay, so I think we've got 94% of people saying B, which is again the right answer. So I'm just going to take one really common Slido question that I see kind of popping up is, so sort of just to reference the exact questions, do you know or any free / expensive version control software for CAD? I think I kind of answered this one. So yeah, I think just in general, SolidWorks PDM is expensive, but apparently it's good, but you definitely need a server to work it. So my recommendation would be Onshape. If you really don't like Onshape, then my second one would be Fusion 360. I've used both. They work on both Macs or PCs. They're very fluid softwares. They're good for beginners. Onshape is a little different from other basically industry PDM styles of them working, but their actual CAD is fairly intuitive. And like I said, once you sort of learn one, shifting to another isn't terrible. So I actually came to Onshape from SolidWorks, and it took me about a day to sort of get acquainted with like the software, and it was totally fine. So my advice would definitely be Onshape, just because it's free. I find it relatively easy to use. It gives you a built-in free PDM way of working. And as well, I've actually seen, like, if you end up working in sort of startup industries, I've actually seen a lot of companies tend to use Onshape just because for them it's actually cheaper as well. So I think that sort of answers this one here. Do you think one should pirate SolidWorks? I would, obviously I'm not going to advocate for pirating, but SolidWorks, I don't think it'd be worth it to pirate it. I would probably say like most universities, so if you're going into a university, will probably have SolidWorks actually available to students. And I think even some universities, I believe even KPU and some of the other bridge programs will actually give you courses almost in SolidWorks. I know UBC does a mini sort of course in SolidWorks for all engineering students, and then again for mechanical engineering students. So I wouldn't worry about pirating it. It's just more about getting used to CAD. And even if you are familiar with a lot of other CAD suites and a job, or in the future you need to work with SolidWorks, like I said, it wouldn't be hard to pick it up. And I think that, so are there any open source CAD software that are widely used in industry? Definitely depends on the industry, but open source, it would generally probably be Onshape. The thing is that even those, like a lot of CAD softwares, once they're actually used by firms, the firms don't really like it. So, sorry, the softwares don't really like it. So essentially they charge them. I think that covers what I was hoping to. Oh, and someone said, please tell everyone that the AutoCAD and the entire Autodesk suite is free for 3 years for any student. So that's an option as well. Okay. So we're already at 3:49. So I'm going to give a brief introduction to rapid prototyping and 3D printing. Luckily, we're already through the bulk of the presentation. So what is rapid prototyping? So rapid prototyping is a tool available to designers working with physical components that is primarily used during the concept evaluation, development, testing, and implementation stages of the design process. By the way, sorry, I actually forgot to mention one last thing. In terms of Onshape, after this presentation, I know this presentation was scheduled from 3 to 4, but I'll stick around in the Zoom chat, and if there's enough interest, I'm actually going to do a little mini guided session with Onshape. Definitely not as structured as the presentation, but sort of introduce you to what it is and if people wanted to get started with that until about 5 p.m. So if people got to go, totally fine. But yeah, if you're interested in that, that'll be available. Okay, yeah, continuing on with rapid prototyping. So again, this is used in a lot of the same stages that CAD is being used for, and it's often used in tandem with CAD. So rapid prototyping is essentially the fast fabrication of a physical part or assembly with the aid of CAD. So you're generally going to model a part in CAD first, and then you're going to take that part and say you need to test it in the real world. So like I say here in professional engineering practice, this can be used from either just prototype testing, whether you're going to fracture test it, see how it bends, see how it breaks, see how this interacts in a part of a system, or if it's like a smaller company, or depending on the part itself, I've seen rapid prototyping become a part of the manufacturing process itself. So that's another option as well. But it's definitely a technology that's sort of growing within industry. And why is it growing so much? Is because it allows people and engineers to manufacture with a lower barrier to entry / learning curve. So before rapid prototyping was a thing, in order to sort of manufacture these parts, you have to machine them, and machining takes years and years of practice to learn how to do properly. So to be a reliable machinist working to millimeters or even lower of precision takes years of practice. So being able to automate these processes and basically train engineers to prototype their parts within days or weeks is huge, and it allows a lot more people to prototype and a lot more people. So for example, with the COVID pandemic, we saw that people, even non-engineers, but students, were able to sort of develop reusable products with just 3D printers. So what are examples of rapid prototyping technology? Basic machining, that's one. So not the super high level machining that you're going to get into if you're actually a machinist, but a very basic lathe, mill, bandsaw. If anybody of you guys have taken wood shop or metal shop in high school, you'll be familiar with some of these, hopefully. Hand tools, I guess, counts as well as rapid prototyping. So using like shears with some sheet metal is technically rapid prototyping. Spot welding is another one that's fairly easy to learn. Water jet cutting, laser cutting, and 3D printing. You may or may not have had access to water jet cutters or laser cutters in the past. I remember actually in my high school, we were lucky and we had a laser cutter, which is super useful and a really cool piece of technology. So these images here on the right, we've got a water jet cutter. This is, both of these images are credit to UBC. So this is in the UBC machine shop. So mech students, I think manufacturing engineering students as well, and one other engineering, I forget, has access to this machine shop. And they have a water jet cutter there, so you're able to actually fabricate parts there. And as well, they have sort of lathes, mills, bandsaws, even for metal. So quick check 8. True or false? Rapid prototyping is the only way to manufacture a part. Okay, so we're at 94% of people getting it right. It's false. Rapid prototyping is not the only way to manufacture a part. Like typically when you're actually getting to implementation levels of the design process, you're actually going to be having a completely different setup to manufacture a part. It's just one way that you can use to quickly fabricate a part. Okay, so where does this lead us into 3D printing? So it is one of these methods of rapid prototyping that we talked about. It's probably the most accessible because water jet cutters and laser cutters are in the tens of thousands of dollars range. So it's definitely one that's gotten really popular. So for those of you who don't know, 3D printing is one specific method of additive rapid prototyping to quickly and cheaply create a part. And that's either for prototypes or for final production. So additive rapid prototyping, I forgot to distinguish this. So something like laser cutting would be subtractive rapid prototyping, where basically you're taking a sheet or a part or a metal and you're taking away things to make your part. With 3D printing, you're essentially taking the material and building it into the part. So there are different types of 3D printing with different advantages and disadvantages. And something to know is that the technology has evolved from being relatively industrial. So when I was younger, 3D printers with thousands of dollars, and even FDM 3D printers. Oh, sorry. Whoa. There we go. So there was not really any access to them for most people. However, I've even seen 3D printers in libraries now. So most people might have access to a 3D printer, which is actually really cool to see. So common types of 3D printing. Fused deposition modeling, or FDM. This is probably, if you've seen 3D printer work, you've probably seen a fused deposition model or FDM printer. So this is the most common. It's basically you're melting material, PLA or ABS, into layers and fusing it into a part. So essentially it's just going to take a really hot iron almost and basically melt the plastic and do so in layers over and over and over. And that plastic is going to melt together and basically make a part. So it's the cheapest, it's the fastest, and the easiest, obviously dependent on the design, but most likely it's going to be the cheapest, fastest, and easiest option. However, it is also the least sturdy and lowest, I say quote unquote quality prints. I mean, if your quality is looking for cheap or for fast, then obviously it's going to be high quality. But if you're looking for a really nice part that's smooth, got a really nice finish, that kind of thing, you can make really nice FDM prints, but it's not going to be the best method to do so. What would probably be either SLS or SLA printing. So SLS is selective laser sintering. And so instead of using basically strands of this plastic and melting it together into layers, it's essentially taking powder of that material and then using a laser to bind the material together, again, basically through heating it up and letting it cool. It's a lot more expensive than FDM printing. It's a lot slower, and it's generally harder to get access to. However, the prints are a lot higher quality, quote unquote, and they're much sturdier. They generally are, harder to break, that kind of thing. SLA is kind of similar to SLS. It's just using liquids or resins rather than using powders of the chosen material. SLS and SLA also give you a lot more option to different materials, which I don't think I'm actually going to get a chance to talk about due to sort of time constraints. But choosing the material that you want when you're actually manufacturing a part is actually really important. So SLS and SLA would generally give you more options in that sort of sense. So when and why to use 3D printing? So this is another thing, is that we just talked about how rapid prototyping isn't the only option. So when would you typically want to use rapid prototyping, or specifically 3D printing? Number one, if you need a part fast and cheap. If you just need to test something, if you just need to see how two parts interact, 3D printing could be a great option for that. If you need to get a feel for how the part will act and look in relation to other parts in the physical world, sort of what I just mentioned, that's another thing. Physical testing, another one, if you need to manufacture a complex shape. So like I was saying, when you're designing, you generally have to keep in mind what sort of manufacturing method you're going to do. So certain things can be manufactured on a 3D printer compared to other things. However, not if your part is subjected to high heat. Obviously, if you're binding things together using heat, you subject it to more heat, that stuff's going to melt. It's not going to stick together anymore. It's not for production or use if the part needs to carry heavy loads. Maybe with SLS printing, you might be able to make it work, but you're not going to make a house concrete like beam or like a beam to hold up a really heavy structure out of 3D printing. It probably won't work out too well. And not if there's a better manufacturing available for the specific situation. For example, if you're just trying to make a wooden plank, you wouldn't go out SLS and print wood to make a plank. You would probably just go buy a plank. So that's probably the better option there. So that's generally 3D printing. And I think that's actually, how to get started with 3D printing. So I apologize, I'm just gonna run a little bit over. Probably a best idea to become familiar with CAD first, since most of your workflow is going to begin there. And then after that, you'll convert it into an STL file. So like I said, Maker Labs, they're available throughout the Lower Mainland. There's a couple in Vancouver, I know. Schools also have, even high schools will have access to 3D printers. I think a lot of them do now. Or you could purchase one. I think there was someone mentioned on Slido, what's a good one? If you look at the Ender 3, ENDER 3, that's a relatively inexpensive-ish one. That's generally high quality. And I've seen a lot, I've had experience with it. It's a pretty good printer. So that's one I'd recommend. And after that, you can pretty much have fun. I mean, you can make a lot of things with 3D printers and CAD generally. So yeah, if possible as well, have someone train you on the specific printer you're going to be using, or if you're purchasing one, make sure you read the manual. They can be reasonably delicate, so you definitely don't want to break a couple $100 worth of equipment on your first go. So do be careful, but definitely give it a try, especially if you have access to a public one, or if someone else in your household owns a 3D printer and will let you use it. So quick check 9, SLS is the most common type of 3D printer. All right. So we actually got a couple of like a heavier split here. So the answer was B, false. Like we said earlier, Let me go back here. Fuse deposition modeling is definitely the most common type of 3D printing. SLS is a lot less common, mostly because it's more expensive. Quick check 10. In order to 3D print, you need to be able to use CAD to model your intended piece, have access to a 3D printer, options A and B, and D, own a 3D printer. All right, so we had around 80% of people getting it right. You need to be able to either have someone else model in CAD for you or be able to model in CAD yourself and have access to a 3D printer. So the correct answer here is C, options A and B. You don't necessarily need to own the 3D printer that you're using. All right, so that's pretty much what I got for people today. So CAD and rapid prototyping are both great tools for designers, and they can be used most powerfully in conjunction to help designers throughout many stages of the design process. Practice is critical. So the more experience that you get with them, the more you'll be able to expedite your designs and know where not to use them. I'm happy to stick around and answer a couple more Slido questions. And then, like I said, after that, so I think I'll probably do like a 10-minute break. And then after that, I'll come back. But yeah, thanks everyone for coming out if you're not sticking around. And then after that, I can answer some more Slido questions and maybe show you guys a bit of Onshape if that's something that people would be interested in. Here I'm going to take, there's still like a couple Slido questions, so hopefully the people who are asking these are still around. So someone asked, what advice do you have for those interested in working for WSP in the future? That's a great question. I think number one, Revit and AutoCAD were like, if you're looking for software that maybe you could learn, across the board, whether it was the electrical team, the mechanical team, structural, they definitely really cherished people who were good with Revit and AutoCAD. So if that's sort of like what you're looking for, like what CAD software, if you're looking at WSP specifically, but in general, it was a really fast-paced environment. So I guess be comfortable with a fast-paced environment because there are a lot of projects that are sort of coming in and you're working on. And as well, another thing is that if you're really interested in working at WSP, it's always great to reach out. So one thing that I learned looking for co-op jobs is honestly, there's no shame or anything like that. It's actually really, really good to show your interest and you can even send them an email and just sort of say like you're really interested in working in so-and-so like department, or like in this, like say you're working in civil engineering, really interested in the structural team. You know, would it be possible to arrange a tour or something like that and be able to show your interest in working? And then on the plus side, you also get a tour. So it'll be a cool experience. And I do remember when I was there, we did actually have, I think, a first-year university student was taking a tour and was looking at a co-op, sort of what life of a co-op would be like at WSP. So if you are really interested, that's one way to go. These two are kind of related. So have you seen mechatronics engineering, such as at SFU, or how much crossover is there between engineering specializations? So lots of crossover. So definitely like a mechatronics engineer, one thing that you'll learn is that experience is sort of king in the engineering world. So if you're a mechanical engineer and you have a lot of experience in mechatronics specifically, you're going to definitely be able to find a mechatronic. to the extent where, for example, one of the best software engineers I know, or someone who's been doing lots of software internships, is actually in a civil engineering program. So definitely, if you're in mechatronics engineering, I've seen mechatronics engineers work alongside the same sort of teams that I would work on, compete for the same jobs that I would look at. So definitely, there's no downside. I would say the only thing that you're going to be looking at is sort of where you're starting your career, maybe. So if you're looking at like robotics or mechatronics, then that's definitely a great career path. However, if you go into mechatronics engineering and say you want to do an aerospace job, for example, you might not have as much of the fluid dynamics or thermo, like basically the physics knowledge that a standard mechanical or a thermal fluids mechanical engineer might have. And in that case, having experience, personal projects might help sort of level the playing field there. So in terms of crossover, there's definitely lots of crossover. So mechanical engineers are involved in a lot of biomed stuff, particularly because mechanical engineering as a discipline is sort of involved in a lot of things. Whenever things are moving, you'll probably find a mechanical engineer. So definitely, if you're in mechatronics or mechanical engineering, you can definitely be in biomed, and you can definitely have mechatronics engineers in aerospace. Not to drag out the answer too long, but one thing will be that you might see as well engineers who are in mechatronics doing things, for example, in aerospace, I think was your example as well. For example, if they're doing like avionics on an aircraft, so they might not necessarily be designing the chassis of the aircraft, but they might be working on that specifically, like the avionics stuff. So I do as well know a mechatronics engineer out of UBC who did a 1-year internship with Airbus. So definitely, like, your degree or your exact degree is not going to make a huge difference when it comes to experience. What specialization should I choose at UBC Engineering if I want to go into aerospace? That's kind of the same thing. So I don't think it's 100% matters. You could definitely pick general. You could definitely pick mechatronics. Thermal fluids is another option. Maybe not biomed. Like, it might not as 100% relate. But again, like, say you're even a biomedical specialized engineer, like mechanical engineer out of UBC, and you have experience with an aerospace design team, you've just like worked with aircraft, you have internship experience at an aerospace company, no doubt you'll be able to find work at an aerospace company.
Thank you, Adam, for your presentation. Unfortunately, we'll have to wrap up the Q&A session. If you have any unanswered questions after the Q&A period has finished, feel free to contact Adam through his email, which is sent into the chat. With that, I'll be passing it back to Sophie to wrap up the workshop.
Okay, thank you so much, Adam, for your amazing workshop. On behalf of our entire team, thank you everyone for joining us. This workshop would not be possible without you being with us here today. SRIL is a rapidly growing youth organization specializing in robotics and STEM education. In 5 years, SRIL aims to be the Center for Innovation in BC. If you would like to take part in innovation projects or engage in STEM education and outreach, SRIL team applications open later this month. For more information, please go to our social media and website. If you're interested in seeing Adam doing a CAD demo, please vote in the poll below.